Welcome to the second part of 11th Physics Chapter 9, Mechanical Properties of Solids. In this part, we will study about the topic strain in detail. When a deforming force acts on a body, the body undergoes a change in its shape and size. The ratio of the change in any dimension produced in the body to the original dimension is called strain. So mathematically, strain will be the change in dimension divided by original dimension. As strain is the ratio of two like quantities, it has no units and dimensions. Types of strain. Longitudinal strain, it is defined as the increase in length per unit original length. When the body is deformed by external forces, longitudinal strain is equals to change in length divided by original length, and that is delta L divided by L. Shearing strain is a measure of relative displacements of two opposite faces of the body as a result of shearing stress. So mathematically, shearing strain will be equals to tangent of the theta, and the theta is shown in the figure. Mathematically, relative displacement between two parallel planes divided by the distance between parallel planes. Volumetric strain. It is the change in the volume per unit original volume when the body is deformed by external forces. Mathematically, volumetric strain is the change in volume divided by the original volume. Hooke's law. From experimental investigations, Robert Hooke formulated a law known after him as Hooke's law, which states that the extension produced in a wire is directly proportional to the load applied. He pointed out that the strain is proportional to the extension of the wire and the stress is proportional to the load applied. Therefore, modified form of Hooke's law to more general form is within the elastic limit, the stress is directly proportional to strain. Thus, we can say that within the elastic limit, stress is directly proportional to strain. And when you will remove a directly sign, you will get a constant. And that constant K is the constant of proportionality and is known as modulus of elasticity. Here, by the term elastic limit means if a small load is suspended from a wire, its length increases. When the load is removed, the wire regains its original length. But if a sufficiently large force is suspended from the wire, it is found that the wire doesn't regain its original length after the load is removed. The maximum stress within which the body regains its original size and shape after the removal of deforming force is called elastic limit. And if the deforming force exceeds this elastic limit, the body acquires a permanent sit or deformation and is said to be overstretched. Experimental verification of Hooke's law, as shown in the figure, suspend a metallic spring from a rigid support and attach to its lower end a pen and a pointer. Arrange a scale in the vertical position so that the pointer is able to move along it. Read the position of the pointer on the scale when the pan is empty. Place a weight of 50 grams, say, in the pan and note down the position of the pointer on the scale. The difference between the two readings gives the extension produced in the string by the weight added in the pen. Increase the weight step by step and note down the corresponding extensions and plot a graph between the extension of spring and the total load producing it. You will get the graph is a straight line. This indicates that extension is directly proportional to applied load, and this verifies Hooke's law within the elastic limit. The modulus of elasticity or coefficient of elasticity is the ratio of the stress to the corresponding strain within the elastic limit. So mathematically, it is denoted by K, or in some books it is denoted by E also. It is stress by strain. The SI unit of modulus of elasticity will be the same as that of stress, that is Newton per meter square. And its dimensional formula will be ml minus 1 t minus 2, because the strain is a ratio of the same dimensions, change in length upon original length, and so on. So you know that it has neither the unit nor the dimensions. Different types of moduli of elasticity. Corresponding to three types of strain, as we have already studied, we have three important moduli of elasticity. Young's modulus, denoted by Y normally, bulk modulus, denoted by K, and shear modulus or modulus of rigidity, denoted by eta. Young's modulus of elasticity. Within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is called Young's modulus of the material of the wire. Mathematically, Y is equals to longitudinal stress divided by longitudinal strain. By putting the value of longitudinal stress and strain, you will get F by A divided by delta L by L, or F into L divided by delta L into A, where L is the original length, delta L is the change in length, F is the weight mg acting vertically downward, and A is the area of cross section of wire, and that is pi r square if r is the radius of the wire. So Y is equals to mg into L divided by pi r square into delta L. In this way, you can calculate the Young's modulus, and in numerical problem, you have to use this formula and just put the known values to you. You will find the unknown value. Thus, if L is 1 meter in this formula, area is 1 meter square, delta L is 1 meter, and then Y will be equals to F. Thus, Young's modulus of elasticity is equal to the force required to extend a wire of unit length and unit area of cross section by unit amount. That is the force required to double the length of the wire. If Young's modulus is more, to produce a small change in length, more force is required. SI unit, Newton per meter square or Pascal. Metals have comparatively greater Young's modulus. That means to change the length of metals, greater force is required.